Welcome to Spring LIB.
In this exercise, we're going to be talking about circular motion, and also we're going to use the concept of radius of curvature. So I'm briefly going to review these concepts before we dive into the exercise. So first, when a particle is undergoing circular motion, we can decompose its acceleration into two components. So the first one is a centripetal component that points to the center of the circle trajectory. Okay, this is the centripetal acceleration and the tangential acceleration that is tangential to the trajectory. The centripetal acceleration is equal to v squared over r, and it accounts for the change in direction of the velocity. The tangential acceleration, on the other hand, accounts for the change in speed of the velocity. Notice that the centripetal acceleration can exist even if the speed is constant. Okay, and for the concept of radius of curvature, consider that we have a certain arbitrary curve, and we want to know the radius of curvature of this curve, y, x, in a certain point, x0. What we should do? Well, in order to find r, which is the radius, I'm going to take 1 plus the derivative of y with respect to x, calculated at x0 squared to the 3/2 divided by the magnitude of d2y dx2. Okay, so now we are able to solve the exercise. So what we have in the exercise is a car that is making a parabolic trajectory as shown here in the picture. Y equals 20 times 1 minus x squared divided by 6400. And at the point shown here in the figure, x equals 80 meters, we have that the speed v of the car is 9 meters per second. Its acceleration downwards is equal to 3 meters per second. And the mass of the car is 0.8 megagrams, which is the same as 800 kilograms. So our goal is to find what is the frictional force that the road exerts on the car, and also what is the normal force that the surface exerts on the car. In order to find these things, I'm going to draw here a free body diagram. So here we have the car. This rectangle represents the car. And the forces that act on the car are the gravitational force that acts downwards, also the normal force, and the frictional force. And this angle that the frictional force makes with the horizontal, I'm going to call theta. Okay. Now I'm going to decompose these forces into two components. One that is centripetal, that points to the center of curvature, and another one that is tangential. Okay, and I'm going to call these coordinates r and theta. So in the r coordinate, what we have is mg times the cosine of theta minus the normal is equal to m times the centripetal acceleration, which, as I said, is v squared over r. In the theta coordinate, the tangential coordinate, we have mg sine theta minus the frictional force is equal to m times the tangential acceleration. Okay, so notice that there are two things here that we still don't know. We don't know what r is, we don't know what theta is, and of course we don't know what m and the frictional force are, but that's what we're going to find out. So first, let's find what theta is. Okay, so basically we have this curve here, and this angle is theta. Now the tangent of theta is equal to minus the derivative of y with respect to x. And the minus is here because the curve is decreasing. This means that the angle theta, if we didn't put the minus here, would be negative. We don't want that. Calculated at x equals 0. Okay, so theta is the arc tangent of minus dy dx at x0. Actually, it's not at x equals 0, it's just x0. Now the derivative of y with respect to x, if we take the formula that we have for y up here, is 0.00625 times the value of x0, which is 80 meters. So theta is equal to 26.6 degrees. Also, we have to find the radius of curvature. In order to find the radius of curvature, we need dy dx, which, as I said, is minus 0.00625x, and d2y dx, which is minus 0.00625. So we want to find r, and that is 1 plus minus 0.00625 times 80 squared to the 3 halves divided by 0.00625. So r is equal to 223.6 meters. Now, given this, we can go back to the equations for the two components and find both ff and n. Let's start with n. Okay, n is equal to m times g cosine theta minus v squared over r. So we have that m is equal to 800 kilograms. G is 9.8 meters per second squared times the cosine of 26.6 degrees minus v squared, so that is 9 meters per second squared divided by the radius of curvature, which, as we found, is 223.6 meters. So n is equal to 6.72 kilonewtons. Okay, we also have to find ff. Remember that the acceleration is 3 meters per second squared, the tangential acceleration, which, as I said, is the rate of increase in the speed. So we have that ff is equal to m times g sine of theta plus, actually minus at. So what we have is m, which is 800 kilograms, times 9.8 meters per second squared times the sine of 26.6 degrees minus 3 meters per second squared. So ff is equal to 1.11 kilonewtons, which concludes our exercise.